we will be discussing the problem in Pitel's book at page 137, number 3.52. At a certain time during a hurricane, the wind pressure acting on the wall of a high-rise building varies linearly as shown. Determine the resultant force caused by the wind. Let us first identify the required in this problem. Since we are given the distributed load at this figure, then we would be needing to take account the area of application in the system. We can see that the area affected by the distributed load changes at an altitude of 180 feet. So, we will have to divide this system into two different systems, which consists of two different rectangular prisms. Now, let us evaluate the distributed load on our larger prism. As we can see, we don't know the value of the distributed load at the 180 feet altitude. We will have to establish a relationship for the distributed load. First, let us separate the rectangular component of the distributed load from the triangular component. Then, let us analyze the triangular component of the distributed load. As we can see, our unknown and the 3.2 pound per foot squared will be located at the shorter leg, while the altitude will be located at the longer leg. Since we need the value of the unknown in the shorter leg, we can use a trigonometric function that utilizes the two legs of the right triangle to solve for the angle. We can either use tangent or cotangent to solve for the unknown. Doing so, we will get the unknown as 0.84 pound per foot squared. Now, we already know all of the present load in the distributed load. We can now replace the distributed load with a concentrated force. Since it is not rectangular or triangular, we are to divide it into pieces. After dividing it into pieces, we will be able to make a two-piece which is rectangular and triangular. Since it is in 3D, we are to analyze it into axes. First, let us analyze the triangular part. In this shape, when making it into a singular force, we are to place the singular force in the middle of the x-axis, and 2/3 of the height in this problem since the distributed load is vertical. Next, we evaluate the rectangular part. In this shape, we always locate the singular force in the middle of the area of application of the distributed load. Now, we already know where it is located. Let us then compute for the amount of force present in those forces. In order to get the force in the system, we are to find the area of the shape, like so. Now, let us do what we have done with the larger rectangular prism with the smaller. After doing so, we will find this answer. Now that we know all of the forces that acts on the system, we can now solve for the resultant force, which will be equal to the summation of all the forces. After that, let us get the moment of each force with respect to any point. In this video we will be using the origin as the moment center. Before we can solve for the moment, we must first identify the distance of the moment center from the forces in vector form. After we get them, let us get the cross product of the force and the distance that we were able to get, like so. This is just the continuation in solving for the moment. Now, we already have the value of the moment of each of the forces at point O in the definition of moment and forces, that the resultant moment is equal to the cross product of the distance and the resultant force, and it is also equal to the summation of all the moment of each force in the system. Since we already know the moment of all forces, we now need to identify the equation of the resultant moment, so we could get from the cross product of the distance and the resultant force. We will get that equation by multiplying the solved resultant force with the unknown distance that we could name as xi plus yj plus zk. The cross product will yield to this equation. Now let us equate the equation that we were able to derive with the summation of all the forces in the system, which will give us to the point of action of the resultant of the forces caused by the distributed load of the wind, which is X is equal to 59.1 feet, Y is equal to 0, and Z is equal to 135.6 feet.